Hello, college prep chemistry students. Today we are going to look at the kinetics of a chemical reaction. When we say kinetics, we're thinking about movement. So how fast do atoms and molecules react? That's what we're thinking about, them coming together. All right, we'll be thinking about the speeds of reactions. So I just have a couple of examples of a couple different races, right? So we have stock car racing, right? Those cars go really fast. We have runners on a track, right? Looks like they're doing a sprint. And then we have turtles, right? Some people race turtles. In all three of these examples, the pace is much different, right? The speed that the different people or the different objects are going at is much different. And that's something we want to think about with a chemical reaction. All right. Some chemical reactions, like the race cars, are really fast. Some chemical reactions, like the turtles, are very slow. So we're thinking about how quickly a chemical reaction takes place. So the first example I want to give you is metal rusting. All right. Metal will rust, especially if it's left outside. All right. So a lot of old cars, if you were ever to buy a used car, you would want to try to look at how much rust there is on the frame, things like that. We can't really undo rust, right? So that's really difficult. So you never want to buy something that's super rusty. Even if you bought a brand new car, over time it will rust. All right. You can leave it inside, you can do all these different things, but over time it will happen. So that rusting reaction, it's typically a very slow reaction. All right. Certain cars are really bad where they rust out quicker than others, and that is kind of a design flaw. But again, we have this example of this beetle here, and it is quite old and it is quite rusty. Now, I also have pictures of MREs. All right, those are meals ready to eat. They use them a lot in the military. And those are meals that can cook themselves. Now, they have a packet inside where a chemical reaction takes place, and that chemical reaction releases a lot of heat and it kind of cooks the meal, right? So that's the MRE, ready to eat, right? So it can essentially cook itself. It uses the exact same reaction as that rusting reaction. So we want to think we're seeing the same chemical reaction, but in the MREs, it happens very quickly, right, when it's allowed to happen. And in the car, it happens much slower. So that would be the kinetics of it, how fast the reaction is occurring. So we're going to look at two theories as to how a chemical reaction takes place. There's the collision theory and there's the transition state theory. All right, they're both theories. They're trying to explain the chemical reactions that we observe. And each theory has its strengths and its weaknesses. We'll look at both. We'll use both. All right. So it's not like we're going to pick one and decide that's our favorite theory. All right. We're going to use both. They're both a different lens to view these reactions. So the collision theory we'll start with. And what that name says, you want to think the atoms or the molecules, they have to physically collide. They have to hit for the reaction to take place. All right. So we're going to get these collisions between atoms, collisions between molecules, and not all collisions will be fruitful. So the collisions between molecules, they have to have sufficient energy to break the bonds in the reactants and then form the new bonds in the products. All right. And the molecules, they're also going to have to collide with the proper orientation. Right. So it's possible that two molecules can hit, but if they're not lined up properly, they'll bounce off. All right. And if they don't hit with sufficient energy, they will again just bounce off. All right. So we have this example here. We have N2 and O2. They collide with the proper orientation. They have the sufficient amount of energy, and we get two NO molecules that separates from that collision. So again, a fruitful collision, proper orientation, sufficient energy, we get this activated complex, but then we get the products. An unfruitful collision, either it doesn't have the right orientation or it doesn't have enough energy, and they just bounce right off those molecules. All right. Now, a head-on collision is going to have more energy than kind of like a glancing blow. So When we have a system, we're going to have, again, just millions and millions of these molecules, and there's going to be collisions happening everywhere. They're all going to be bumping into each other, and a lot of those collisions will have no reaction, but some of them will have the proper orientation, the proper amount of energy. They will lead to the product. All right, so there's going to be a lot of collisions before we get to the final spot. It's kind of like if you've ever been at like a school dance or a party or anything like that, where there's like some game going on and everyone's bumping into each other, and you have to find like a partner, right? Like a DJ will play that at different events, Sweet 16s, things like that, and you're looking for a partner. Just even if that doesn't work, think about just walking in the hallways, right? You bump into a lot of people, so there's a lot of collisions happening, but there's no reaction occurring, right? But then maybe you see your friend and you high five each other, and your hands are in the proper orientation, and you hit it with enough energy, right? And we get that product of that friendship. All right, so that's our example. So again, just to reiterate, if they're moving too slow, we're not going to get a reaction. And if they're not lined up properly, we're not going to get a reaction. It has to be both, right? It has to have the right amount of energy, and it has to have the correct orientation. So we can even see reactions happening in multiple steps, right? So two molecules might have to collide with another, and they'll make some intermediates, and that intermediate, this is what I'm looking at, right? I'm circling it. That intermediate will then be used in a later step, right? So even in the collision theory, a reaction can occur in multiple steps, all right? Some of our more complicated chemical reactions, they don't happen all at once. They happen in multiple steps, and it's multiple collisions that have to occur before we make our final product. All right, so that's the collision theory. They have to bump into each other, and there's two important pieces to it: orientation and energy. Now we have the transition state theory, and it's going to have this unique graph, and we're going to see that graph a lot. All right, so this graph, it's an energy profile. We're looking at the potential energy going up, and I'll talk a lot about potential energy in a later video, but for right now, it's going to be the energy of the reactants, the energy of the products, and then down here, we have the progress of the reaction. So to go from reactants to products, we're going to have to move through this transition state. All right, so the potential energy will change, but we will go from left to right, from reactants to products. Now, a lot can happen in these profiles. We'll be looking at these profile diagrams again in the next video. We don't have to worry about the height of the reactants or the products. We don't have to worry about the potential energy. What we really want to worry about is this EA. All right, that is called the activation energy. That's the important part of the transition state theory. It's the activation energy. So what does that mean? Activation energy is the energy it takes in this theory for a reaction to occur. All right, so we kind of think of it as like a hill. We have to get the reactants over that hill, right? We have to give them enough energy over that hill, and then they will form the products. All right, so if we think of the Greek myth of Sisyphus, he has to just keep rolling a ball up a hill, and then when it reaches the top of the hill, it rolls down. So in a chemical reaction, if we put in enough energy to get to the top of the hill, it'll roll down and it'll form the products, right? So we have the reactants need the activation energy, and then they roll down and form the products. Now, at the top of the hill, we call that the transition state. All right, so kind of like the collision theory, we have these reactants. When they come together after they've received the activation energy, they have this temporary transition state where they're all kind of connected, and then they separate apart, right? So our final state is our product. So we have the red, the black, and the green by itself. In the transition state, they're all connected. And then in the products, the black and the green are the new product, and the red is by itself, right? Nice single replacement reaction we're looking at here. So we have the activation energy. That's the most important part of the transition state theory. All right. Again, we can get these different transition states. They are not real molecules. They're just temporary spots while the reaction is taking place, right? So these are HI molecules. Here's the temporary transition state where everything is connected, but now we have the pure hydrogen, the pure iodine by themselves, right? So that transition state, it is temporary. It's kind of like when someone asks you to hold something for a second and then you hand it right back to them. All right. And again, this can happen in multiple steps. So we saw that with the collision theory, it could be multiple steps. In the transition state, a reaction can be multiple steps as well. It's multiple activation energies. All right. Now, the higher the activation energy is, the harder it is for that reaction to take place. So in this example, um, once you reach that amount of activation energy, you'll get through the next one pretty easily, all right, because it's lower. It's lower on our potential energy diagram. So how to speed up chemical reactions, all right? There's a couple of different ways, and we're going to go through all. There's 4 main points. We'll go through all 4, and we'll look at them in the lens of these 2 different theories. So how to speed up chemical reaction? You can increase the temperature. You can increase the concentration. You can decrease the particle size, and we will call that the ability to meet, and you can add a catalyst. So increasing temperature, all right? Let's think about this from the perspective of the collision theory. If we increase the temperature, right, the particles move faster. Their temperature is really how fast the particles are moving. So at a low temperature, there's often not a lot of collisions that produce a reaction. At a higher temperature, you're going to get more collisions with that sufficient amount of energy, all right? And you're going to get more successful collisions. So let's just think about a simple chemical reaction, all right? If you leave your milk out, it will spoil, all right? So where do you need to leave the milk, all right? You put the milk in the refrigerator so that it's at a lower temperature, there's less collisions, and so that milk doesn't spoil. Now, it will spoil eventually in time, right? So even though we can slow down the reaction of milk spoiling, if we don't drink it quick enough, it will eventually go bad, all right? Whereas if you wanted to speed up a reaction, you would heat it up. And if you wanted to slow it down, you cool it down, all right? So that is the effect of temperature on a chemical reaction. Now we can increase the concentration. So at a low concentration, there's not a lot of the reactants. So they're not going to bump into each other as often, all right? And then when you have a lot of the reactants, right, when we increase the concentration, we're going to get way more collisions happening, right? So a low concentration, not that many collisions, but a high concentration, you're going to get a lot of collisions, all right? Think about when you're driving really early in the morning and no one's really on the road, all right? That's a good time. I leave for work incredibly early because I don't want to get into a car accident, right? Whereas when you're driving on the parkway and there's a lot of cars and it's that gridlock, right? You're more likely to have a collision occur, all right? The more concentration, the more bumping there's going to be, all right? So then the surface area, all right, the particle size, it's also referred to as, or the ability to meet. Let's think about a solid. All right, if we have a solid, the reaction can only occur on the surface area. All right, so you have these inner atoms or these inner molecules that can't react until they're exposed. Now, if it's grinded down, perhaps, you know, if it's got a higher surface area, it's going to be easy for the reaction to occur everywhere else, right? So this is the ability to meet. It's easier to meet when there's a higher surface area. All right, now our last one, it's the catalyst. And it's possible, you may be thinking, well, Mr. Lopriato, we have used the collision theory to explain 3 of these 4. Why do we even need the transition state theory? Well, a catalyst speeds up a chemical reaction. All right, you'll hear the phrase be a catalyst for change, right? That means make that change happen quicker. So a catalyst speeds up a chemical reaction. But how does that happen? We want to use the transition state theory to show that. So in the transition state theory, we see that the activation energy, all right, of the uncatalyzed reaction is much higher than the catalyzed reaction, all right? So the catalyst allows for there to be a lower activation energy, so the reaction can happen easier, right? If there's less energy, if it doesn't take as much energy, it's going to happen much easier. So here's what it would look like, right? The profile with them overlapped, right? So in the red, we see without the catalyst. In the green, we see with the catalyst. It makes for less activation energy. How exactly does that happen? It provides an alternate pathway. It's almost like a shortcut, right? So the uncatalyzed pathway has that high activation energy, but the catalyzed one, it provides almost like a shortcut, a different way to go. The catalyzed pathway often includes intermediates, which is totally fine. We could have multiple steps along the way, all right? But that's the catalyzed pathway. All right. And you may remember from your biology class, you talked about enzymes. Enzymes speed up certain biological processes. Those are chemical reactions taking place in the body. All of those enzymes are catalysts, right? They speed up the chemical reaction. All right. So, again, how to speed up chemical reactions? You would want to increase the temperature, increase the concentration, decrease the particle size. That again, we call the ability to meet, and add a catalyst. So that is everything you need to know about chemical kinetics. In the next video, we will really look at potential energy and those potential energy diagrams.